All right, so we're going to actually start something that's quite new today. It's called inequalities. It's very much like equations. Um, yeah, you'll see it really builds off a lot of the skills that we've been building lately. So it's not something totally revolutionary or new, but it certainly is going to seem like something a little bit more refreshing today. So here we go. Today's plan, we're going to start with just a really quick review of Chapter 8, that was solving linear equations, and then we're going to introduce, of course, inequalities, which is Chapter 9 in our textbook. And then, of course, just practice, practice, practice. There's a lot of practice that comes with these because it is a bit of a new idea. I don't think you would have ever seen these in previous math courses. I could be totally wrong. Anyway, let's get going. I won't waste your time here. So let's start by solving some equations. I'd appreciate if you just pause the video right here, jot these questions down, and give these a try, and I will go over them in just a second. Okay, so hopefully we're able to give those a try. Honestly, it's really good practice. Just do it in earnest, right? It's a good way of just building some confidence here. But of course, to start these ones, you could use that trick I taught just the other day, where to get rid of the fractions, you could just multiply everything by everything else's denominator. So I'll start with this one. We can just multiply by 3 to get rid of the denominator there. But since you took care of this term, you got to do the same thing on all these other terms too. So we'll multiply both of those by 3 as well. Likewise, we want to get rid of this divide by 7 here. So we'll times by 7 right now there. That'll take those out. But we also have to multiply these other two by 7 as well. So for 2x right here, the 3's took care of themselves, but we now have 2x times 7. So that gives us 14x. This equals 12 times 3 times 7. That's going to be quite a big number, I think. So let's see, 12 times 3 times 7. 252 is what that's going to be. And then plus the 7's took care of themselves here. So we're just left with 2x times 3. That would be 6x, because 2x times 3, 2 times 3 is, of course, 6. We got 6x. Now this becomes a much more standard linear equation. To solve this, we just want to get all the x's to one side. So I would minus 6x from both sides. And when you subtract 6x from both sides, that's going to give us 8x equals 252. And then, of course, to get x totally by itself, we just have to divide by 8 on both sides. You could leave your answer as a fraction if you wanted to, but because upon putting this in my calculator, it actually gave me a pretty decent number, I'm going to leave it as x equals 31.5. If that was a repeating decimal, like if that was like 31.58942, blah, 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 I would have just left it as a fraction because that would just be too messy. But in this case, it worked out pretty nice, 31.5. All right, I'm going to go over this next one. A couple different ways you could go about this. You could take this 4 and you could double dip it through the brackets here and then just solve from there. Or you could start by dividing by 4 on both sides to get rid of that 4 right there. Either way, it'll lead you to the same answer. Personally, I think I'd prefer to divide by 4 on both sides. So I'm going to do exactly that. Divide by 4 on both sides. 6 divided by 4 is going to give you a decimal number, but not a horrible one. That gives us 1.5x. Equals 0.45 plus 3x over 5. Because we got rid of the coefficient in front of the brackets just disappear because they're not doing anything anymore. Then I'll use that trick that I just did on the other one. I'll multiply every single one of these things here by 5. That gets rid of this fraction divide by 5. So 1.5 times 5 is 7.5. So we have 7.5x equals 0.45 times 5 is 2.25. And then that's just plus 3x. Next up, of course, we want to get all our x's to one side. So I'll minus 3x from both sides. That gives me 4.5x, because I took away 3x from there. So 4.5x equals 2.25. And then last but not least, we want to get x totally by itself. So let's divide by 4.5 on both sides. This might be a bit messy. Let's see. Actually, I take that back. It's not messy at all. We have x equals 2.25 divided by 4.5 is just 0.5. That's actually a really nice answer. So we'll leave it at that. Hopefully you were able to get those. If you weren't, of course, that's a pretty good hint that you need to be talking to me. You need to come back into the Zoom and say, hey, Mr. Scott, can you go over a few of these examples with me? I seem to be stuck. But if you got them, kudos, good for you. All right, here's a word problem. I want to see if you guys can do this one as well. Haley can run 4.3 times faster than she walks. Okay, 4.3 times faster than she walks. The difference between her walking speed and her running speed is 8.58 kilometers per hour. How fast does she walk? pause the video here, see if you can piece this one together. Be very careful in setting up some equations on this one. Okay, so I'm going to go over this one now. I'm going to start with this very first piece here. I think this is quite interesting. Her running speed is 4.3 times faster than her walking speed. So why don't we say that W represents Haley's walking speed? So then that would mean Haley's running speed, which I'll call it R, is equal to 4.3 W. Now, the difference between her walking speed and her running speed is 8.58 kilometers per hour. Now, clearly she runs faster than she walks. So by difference, we're thinking subtraction, right? Difference is subtraction, sum would be addition, product is multiplication, quotient is division, all that. So difference is subtraction between her walking speed and her running speed. That's going to be her running speed minus her walking speed equals 8.58 kilometers per hour. However, this is two different variables. R minus W, we don't like that. We don't like having two different variables. But the good news is, remember we said R is equal to 4.3 W. It's 4.3 times faster than her walking speed. So how about we substitute that in? We got 4.3 W minus W equals 8.58. Don't fall into the common trap that people just say, oh, it's W, W, those cancel out. It's not like that. It's 4.3 W minus 1 W. That would leave us with 3.3 W equals 8.58. And then last but not least, we have to go 8.58 divided by 3.3. And don't worry, as scary as that sounds, it's actually going to give us a pretty nice number. Her walking speed is 2.6. And I suppose the units on that are going to be kilometers per hour. So that would be her walking speed right there. It didn't ask for her running speed, but if you wanted to calculate it, you could just go 4.3 times 2.6. And that is going to be, let's see here, 4.3 times 2.6. Her running speed is 11.18 kilometers per hour. So there you go. The more you know. Okay, awesome. Moving on. Okay, so now we're starting chapter 9. This is all on linear inequalities. So this may sound different than the last unit, which was on linear equations, but the ideas are pretty much the same. A linear inequality is very similar to a linear equation, except instead of an equal sign, you're using one of these four signs right here. This sign means greater than, and I always thought of it as a mouth trying to eat the bigger number. So if it was something and then this sign and then something, that would mean this thing here is greater than the other thing because the mouth wants to eat the bigger thing. This sign means less than. So in other words, if it was something, this sign, and then something, the second something here must be bigger because it says this is less than this because the mouth wants to eat the bigger number. Now this sign here with a bar underneath it, that's greater than, as the sign would tell you, or equal to. So in other words, it could potentially be equal to whatever the other thing is, and if it isn't, it must be greater than. And likewise, this one down here is less than or equal to. So these four signs are just, taking the place of an equal sign. So instead of having an equal sign here, we have one of these four signs. The basic principles behind solving a linear inequality is the exact same as the basic principles behind solving a linear equation. In other words, whatever you do to one side of an inequality, you can also do to the other, or you must also do to the other to keep things balanced. Let me show you what I mean. Before we get to that, we should talk about how to represent these using number lines. So each of those four symbols represent how x compares to other numbers. We can represent this using number lines. So if we started with x is greater than 3, if we were to plot this on a number line, remember a number line is just a straight line where your smaller numbers are on the left and your bigger numbers are on your right. I always start by making these number lines by taking your focus number of your inequality, so in this case 3, and putting it right in the center. I think we did something very much like this at the very beginning of Math 9 this year when we were doing some Math 8 review. But anyway, so your focus of your inequality goes right in the center, and then make your bigger numbers go to the right. So 4, 5, 6, and make your smaller numbers go to the left, 2, 1, 0. You could even go negative if you wanted to. And now it says x is greater than 3. That means we have to shade all of the stuff that is greater than 3. but we're not going to include 3. So we're going to put an open circle right here saying we're not going to touch it. It's like shielded right here. We're not going to shade around it, but we're going to shade everything that's above it. So x is greater than 3. Now, another really useful tip, I remember this really helped me way back when I was in grade 9. I always like writing my variable like x first, and then my inequality sign, and then a number. And then just to kind of like cheat this, as long as you're keeping to the strategy where you put your smaller numbers on the left and the bigger numbers on the right, I always thought as like this inequality sign as being like an arrow. It's pointing this way, so that's the side you're going to shade. But that rule only works if your x is on the left-hand side. Okay, so it's x is greater than 3. If it was the other way around, like if it was 3 is less than x, which means the same thing because the mouth is still trying to eat the x either way, then that rule doesn't work, right? So just make sure the variable is on the left-hand side. Now, what about this one? X is greater than or equal to 3. Well, this is basically going to be the exact same thing. So I'll draw another number line. We'll put 3 in the center again, and then we'll do 4, 5, 6. Just kind of doing this sloppy here. It's not the end of the world. This is going to be the same thing again. We're going to shade everything above 3. But since this is greater than or equal to 3, we actually have to do a circle that gets shaded in here, because we're actually including 3. So we're shading in where 3 is, and then we're shading everything above it as well, because x is greater than or equal to 3 in this case. Anyway, hopefully that makes some sense. We're going to move on. So again, blank circles versus filled in circles. A blank circle or an open circle is how I prefer to call it. An open circle means greater than or less than, whereas a filled in circle means greater than or equal to or less than or equal to. So here's a bit of a task for you before we move on. Make a number line representing the scenario where only those aged 14 and up may hold learner's permits. Be careful about what sign you're going to use here, and be careful about where you're going to shade on your number line. All right, so I'll go over this. Those who are aged 14 and up may hold learner's permits. That basically just means X, where X represents someone's age, must be greater than or equal to 14 in order to hold a learner's permit, right? So if you're going to make a number line about this, draw your number line right there, put 13, the focus age, right in the center, and then we can do 15, 16, 17, 18, and so on. And then, of course, below that, we've got 13 and 12, 11, 10, and I'll stop there. And of course, because it's greater than or equal to, we're going to put a circle that's actually filled in right here because we're going to include 14. It is totally possible for someone who is only 14 to hold a learner's permit, right? So that is totally possible. Even if you're 14 and a half, or if you're almost 15, or you're 15 or a little older, you can still have it. So we have to shade everything above that. And notice if you use that old arrow analogy that really helped me when I was back in grade 9, the arrow is pointing this way. It all works the same. Whatever floats your boat. Perfect. All right, here's another one. This time I give you the number line and I want you to come up with an algebraic expression. So in other words, kind of like what we did before where I said x must be greater than or equal to 14. We're going to express this one. First of all, the first thing I notice is we have an open circle right here. That means I'm going to be using either a greater than sign or a less than sign because I'm not including this because it's not shaded in. The next thing I'll notice is this number line was constructed correctly with a smaller number on the left and the larger number on the right. So that can automatically eliminate the less than sign because my arrow is pointing that way. So I know the answer is going to be something like x is greater than something, but I have to figure out what this focus number is. They didn't actually highlight it here. And here's what's kind of weird. It goes from 14 over here all the way up to 15 over here. Well, clearly that means there's going to be fractions involved. What I would do is I would try to partition this off into different portions and figure out how many portions there are between 14 and 15. Notice there is 1, 2, 3, 4, 5 partitions between 14 and 15 on this number line. That means each of these would represent 1/5. So we had 1/5 here and then 2/5 here. So we might as well write this as x must be greater than 14 and 2/5. Now, I've been kind of preaching this entire year. We really don't like having mixed numbers in Math 9. So if I were you, I would change this into a decimal. And to do that, 2 over 5 is just 0.4. So 14 and 0.4 is x must be greater than 14.4. And that right there is a really good algebraic expression representing this. If you did put this, though, I would still give you full marks. That is totally okay. Okay, anyway, moving on. Multiple inequalities. Sometimes the variable is suspended between two values. Holy Toledo. The wonders never cease here. To make this a little easier, just read it as x is between the two values you've got. So if we're going to show this on a number line, this example right here, I would read this as x is between 4 and 8, right? So x is being eaten when compared to the 4, but 8 is being eaten when compared to the x. So that means, you know, x has to lie in between these two numbers. If we're going to show this on a number line, it's not really a huge surprise. Set up your number line as we always do with our smaller numbers on our left and the larger numbers on the right. But because there isn't a specific focus here, you have to kind of balance this appropriately. We know x is going to be lying in between 4 and 8. So how about I say 4 is over here, and then let's say 8 is over here. The number that's right in between 4 and 8 is 6, and then we'll have 5 and 7. That's now kind of giving me some space for all of this. So then I can say 9 is over here and 10 is over here. And then saying we got 3 and then 2. Good. Now, the next thing I want you to notice is these are less than signs. They're not less than or equal to. So at 4 and 8, we actually have to put open circles because we are not going to be including those points. The last thing we have to do here is just shade in between those open circles. So from the one open circle at 4 and the other open circle at 8, just shade that area in between. That's about it. That's all we really got to do on this one. Okay. So I want you to try these two. Just be careful on that second one there. There is a mixed number, but the mixed number can be used to your advantage, especially if you go back and look at something like this to see how mixed numbers can be expressed on a number line. Hint, hint, wink, wink, nudge, nudge. Anyway, give these a try. We'll go over it in just a second. Okay, so I'm going to go over this now. First things first, this guy, x is between -2 and +6. If we set up our number line here, remember, make your focus kind of just off center here. We'll say this is 6. We'll say this is -2. I guess the number that's right in between 6 and -2, I believe, is +2. And then between 2 and -2, that would be 0. Between 2 and 6, that would be 4. And you know what? I don't have to make this a perfect scale. You can jump up by 2s each time if you want. There's no rule saying you can't do that. So there we go. We've just got it like going up by 2. Our focuses here will be -2 and +6. And we'll have to use open circles because we're not going to be or equal to that. So open circle here and an open circle here. And then just shade in between. So anything that lies in that shaded area, whoops, didn't mean to do that. What on earth happened there? You know what? I think I know what happened. Can we go previous? Nope, we can't. Okay, I guess just much of my number line just vanished there, guys. Never seen that happen before. Too exciting here. Holy smokes, we're just gonna redo that. I clicked something on my pen and it just totally ruined my world. Anyway, what this basically means is anything that lies in this range is going to be a valid solution, right? So if x lies between -2 and 6, it could be any of these numbers that follow on that number line right there. All right, this next one, 3 1/3, and then we got 5. Those are our focuses here. This number line is going to be a little bit different. Let's be real careful here. I'm going to make it longer just to give myself a little bit more room to work with here. So 3 1/3 is going to be one of our focuses, and 5 is going to be another one of our focuses. I don't feel super comfortable putting 3 1/3 right here yet, so I'm going to go a little lower than 3 1/3 to make it 3. And that seems a little bit more comfortable to me. And I might actually have to change this point in just a second here. So I'm not going to put a circle on the 3 quite yet, because that is not what we're focusing on. We're focusing on 3 1/3. But the number that's right in between 3 and 5 is, of course, 4. You know, big surprise there. And we should divide this each into 3 pieces so we can get those thirds going here. So if we have this here and this here, we've divided between 3 and 4 into 1, 2, 3 chunks. And then we should also divide this into 3 chunks just for good measure as well. And then I guess we can start doing some other chunks past that, but I don't think we'll be labeling anything. Long story short, what I'm trying to ramble at here is this point right here is your 3 1/3. Technically, you don't even really have to label it, but we're going to do it anyway, just so you can see it. But since this is a less than or equal to sign, we need to put a circle that gets filled in right there. And then we'll also need to put a circle that's filled in right on 5. Between these two, we need a shade. So shade from 3 1/3 all the way up to 5. And aside from that, we are golden and good to go. Whew, all right, 2 more. You got to be careful here because these signs are a little bit backwards, but don't fret on this one. It still works exactly the same way. Show each of these on a number line. These are read the exact same way as the other one was. X is between 10 and 4, and X is between -4 and -6 1/4. See if you can come up with a number line on these ones. We'll go over it in just a second. Okay, I'm going to go over this now. This one is a little bit weirder because, of course, our smaller number, for whatever reason, was put on the right. When you design a number line, no matter how they gave it to you, you should always put your smaller numbers on the left. So I'm going to put 4 over here, and I'm going to put 10 over here. And then I just have to think what number lies exactly between 4 and 10. Well, that's a difference of 6, and half of 6 is 3. So 3 plus 4 is 7. And then I guess I can say that's going to be 8 and 9, and that's going to be 6 and 5. That seemed pretty balanced to me. We'd have 3 and then 2. Then we'd have 11 and we'd have 12. Our focus numbers here are going to be 4 and 10. Notice we could also equal them, so I'll put a circle that gets filled in on both of those. And then we just have to shade in between those 2 circles. So even though those inequalities were backwards here, it's the same thing. Just figure out what your boundaries are, plot them on a number line, and then just shade in between. Same goes for this one, but negatives often confuse people. So we got to be really careful here. If we form our number line, and again, I'm going to make it a really big number line because of these, fractions that are going to kind of throw us here. We got to think about what the biggest number here is. The biggest number here is actually -4, because remember, with negative numbers, the smaller value is actually technically a higher number. So I'm going to put -4 way over here. Now, -6 1/4 is actually smaller than -6. So if I put -6 right here, we actually have to go further to the left than that because -6 1/4 is a smaller number. So just for good measure here, and we know between -6 and -4 is, of course, -5. Just for good measure, I'm going to go all the way down to -7. And then, of course, because we're splitting it into quarters, I'm going to say that this is a half, and then these are quarters. -6 1/4 is this point right here, kind of butted up just to the left of -6. If we want, we can also kind of divvy these other ones up into quarters. It's not really a big deal. I'll even put -3 over here just for good measure. It's not a big deal, but again, it is a good habit to get into. But since -6 1/4 is this point here that we're focusing in on, we're going to have to use our circle there. Now, there's one other tricky thing that's happening. Notice between the x and the -6 1/4, we just have a strictly greater than sign. That means with reference to this -6 1/4, we're actually going to use an open circle here. But then on our -4, we have a greater than or equal to sign. So in other words, we're going to have to use a closed circle in reference to that -4. So again, because this did not have a line underneath it when it was butted right up against this -6 1/4, we're going to put an open circle because we will not include this point. We have to strictly have an x that's greater than it, not equal to it. But because with -4, we had a greater than or equal to sign, we can actually shade in this one because x could very well be equal to -4. From there, just shade in between. Same as all the other ones, shade in between. Okay, so it's kind of a different thing than what we've been doing. It was honestly, when I said at the beginning, oh, it's kind of like equations. It wasn't really like equations at all. I was thinking of something else. I don't know why I got ahead of myself. When we deal with these a little later on, you will see that inequalities actually behave very much like equations. But yeah, this was totally something different. So you guys kind of got fooled on that one. My mistake. Anyway, we're almost done here. We've got one last slide. Express the following statements algebraically. That's using, the inequality symbols, and graphically. In other words, using a number line. 3 word problem statements that I'd like you to express. Think about them critically. Jot them down. I'll go over them in just a second. Okay, so the first one, Trey is at least 70 inches tall. So that means he could be 70 inches tall, because at least means, that could be his height, or he could be greater than that. So how about we say if x represents Trey's height, we could say x is greater than or equal to 70. And if you wanted, you can even say 70 inches. This little thing here means inches. Okay, now that's our algebraic statement. We also want to write a graphical statement. So we draw our number line. Since there is only one number as our focus here, it can go right smack dab in the middle, and then put your bigger numbers to the right of it. So 71, 72, 73, and put your smaller numbers to the left of it. We've got 69, 68, and 67. Now, because Trey is at least 70 inches tall, he could be 70 inches tall, so we will put a closed circle right there. That is a possibility for his height. And then we're going to shade everything above 70, because he could be any of these values as well. We have no idea. I can't remember how tall Trey is. I know he's at least 70 inches tall, though, so that's why I put that in. All right, next one. The time Brooke is willing to spend on her homework is at most 30 minutes. At most 30 minutes. So in other words, the absolute most amount of time that Brooke is going to spend on her homework is 30 minutes. So we could also reword this as saying if X represents the amount of time that Brooke is working on her homework, X is going to be less than or equal to 30 minutes. Because again, she might spend 30 minutes working on her homework, but that's the very most she'll spend. She's not going to spend even a second more than 30 minutes. So this is exactly how we could set up our algebraic statement on a number line, very much like the one we just did for Trey. We'll focus in on that focus number, 30, right in the center. Put the large numbers right above it, so 31, 32, 33, and so on, and the smaller numbers below it, 29, 28, 27. This time around, though, X is less than or equal to 30 minutes. Since it could be equal to, we have to put a closed circle here, but we're focusing in on less than that. So we're going to shade this way instead. It could be any of these numbers. She could spend 29, 28, or 27 minutes, and so on. Now, you could really argue on this one if we wanted to go super crazy with this. There's actually a theoretical lower bound to this. At least I hope there would be a theoretical lower bound to this. The absolute least amount of time that you could spend on our homework is 0 minutes. It doesn't make any sense for her to spend negative time on homework. So if you wanted to go a little further with this question, if you wanted to like really push past the boundaries of what you were asked to do, you could make this a two number question by saying 0 is less than or equal to X, which is less than or equal to 30. So you could bound it saying that X is between 0 and 30 minutes. But why? Why would you do that? Honestly, I mean, you could, it'd be nice, but you weren't asked to do that. So don't worry about it. You don't need this. Whatever, no big deal. All right, last one. Leland has forgotten a pencil more than 10 times this year. Sorry, Leland, I didn't mean to pick on you here. But anyway, we're going to write this. It's more than 10 times this year. That means it wasn't just 10 times. It was more than 10 times. So in other words, we have to say if X represents the number of times Leland's forgotten a pencil, we're going to say X is greater than 10, right? Not equal to. It's strictly more than 10 times. Again, I apologize, Leland. I'm not picking on you on purpose. Anyway, moving on. So there's your number line. Put 10 right in the center. We got 11. We got 12. We got 13. We got 9, 8, 7. It's more than 10 times. So we're going to put an open circle at 10. And then we're more than that. So we're going to shade in all these values that are above that. Whew. Okay, that was a long video today, guys. That was over 28 minutes long. So for practice, I want you guys working on these selection of questions. We got page 347, questions 9 to 11, and then 13 to 17, and then 22. So make sure you're getting those done. If you need any help, I am available in Zoom this entire time. Best of luck.